Suppose you are given a system of discrete charge distribution or a system of continuous charge distribution. Can you find out the potential in a simple way without doing any complex mathematics? From our school physics, we know that the potential due to a point charge at a distance r is given by this expression. But do you know that this expression is not a true expression? And we also know about the dipole, that is a system consisting of two equal and opposite charges separated by distance d. And the dipole moment is given by the product of the charge into the distance of separation. And we also assign a direction of this dipole moment, that is from negative to positive direction. But have you ever wondered that why the direction is from negative to positive? Or suppose we are given a single charge, let's say plus q. Can you find the dipole moment for this? Or let's say we have a system of three charges. Can you find the dipole moment for this? So all these questions we are going to answer in this video. Suppose you have a continuous charge distribution of volume charge density rho, and you are interested to find the potential at a point P, which is at a distance r. Then we can take a small volume element, and from volume element to the point P, the distance is r prime, and this volume element makes an angle alpha with the position vector r. So if you want to calculate the potential, then we have to evaluate this integral. Now this integral is very complex, but there is an alternative way where this calculation can be simplified, and that is what we are going to do here. This potential V can be expressed as a series of different components. The first component is the monopole contribution. The second component is the dipole contribution. Third pole is the quadrupole contribution. Fourth component will be the octapole, and this series goes on. Now the interesting part here is all these contributions have a different dependence on the distance r. Here the monopole will depend on 1 by r. The dipole will depend on 1 by r square. The quadrupole will depend on 1 by r cube. Octapole 1 by r4, and it goes on. Now if you see carefully, as you go towards the terms on the right hand side, the contribution decreases because the power of the r is increasing, which is in the denominator. Now we will discuss the first two terms in more details. The monopole term is expressed like this. It consists of a constant term into 1 by r and an integral. Now this integral is very important because this gives the total charge of the system. So if the total charge of the system is 0, then the monopole contribution will also be 0. Let us look at the dipole term. This is the expression of the dipole term. So here also it consists of a constant term into 1 by r square and an integral. Now this integral can be expressed as a dot product of r cap and another integral. Now this we represent it by a p vector, and this p vector, it is what we call as a dipole moment. Now this formula is derived from a continuous charge distribution. Suppose if we have a discrete charge distribution, then we have to replace the integration by summation, and the formula will look like this. Okay, now let us go back to the dipole definition. So a dipole is a system consisting of two equal and opposite charges separated by some distance. And I'm denoting the position vector for the two charges with r plus and r minus vector. Now, using the discrete formula, we can write the dipole moment as this. Here I can take the q common. Now, the expression inside the bracket, we can replace this by a d vector, which is given by triangle law of vector addition, and we can get the final expression of the dipole moment. Now, here we can see that the dipole moment direction is same as the d vector direction, which is from negative to positive charge. And that is how the dipole moment direction is defined. That is from negative charge to positive charge. Let us take another example of a system of discrete charges. But now what we will do is we will try to calculate the potential at a distance which is very far away from the charges. So we can write the potential as this. Now let us try to analyze different scenario. Suppose if the net charge of this system is non-zero, then the dominating term in this expression will be from the monopole, so we can approximate the potential with the monopole contribution. In the second case, suppose if the net charge is 0, but the dipole moment is not 0. So since the net charge is 0, so the monopole contribution will be 0, but since the dipole moment is not 0, the dipole term will be the dominating term, so we can approximate the potential by equating with the dipole term. The third case is where both the net charge and the net dipole moment is 0. So in that case, the potential can be approximated with the quadrupole term. Now let us analyze the basic potential formula, that is the potential due to a charge at a distance r at a point P. So here also we can use the same formula. So we have this formula. Now here the net charge is non-zero. So this integration will be equal to Q. So the dominating term will be the monopole term. So we can approximate the potential by this formula. And that is what we have been using it in our school physics. But this approximation will be better or will be close to the true value only when the remaining terms contribution are very, very less. That is, the distance r is much, much greater than the dimension of the charge body. And that is what we used to refer as the point charge. Now, let us try to find the dipole moment for this system. So we can use the discrete formula. So the dipole moment will be equal to Q into D into y cap. So this dy cap, it is the position vector of the charge. Now what about the potential and electric field? So here the net charge is non-zero. So the contribution of the potential will be dominating by the monopole term. So we can directly say that V is inversely proportional to R. And since we are discussing electrostatics, so we can derive the electric field from the potential by taking the derivative, that is the gradient. So using that logic, we can say that in this case, E will be inversely proportional to R squared. What about this example? Okay, here we have three discrete charges. So using the discrete formula, so P vector will be equal to the QD x cap, that is the charge on the x-axis, then QD y cap, that is the charge on the y-axis, and minus 2 QD z cap, that is the charge on the z-axis. So this is the dipole moment. Now in this second example, the net charge is 0. So since the net charge is 0, the dominating term will be the dipole term, because here the dipole moment is not 0. So with that logic, you can say that V will be inversely proportional to R square and the electric field will be inversely proportional to R cube. This example is very interesting because here we have two different systems. The only difference between these two is the frame of reference. As you can see on the left hand side, the origin is at the center, but on the right hand side, the origin is on the plus 2 Q charge. So in both the system, if we check the net charge, so the net charge is 0 because plus 2 minus 2Q, that is 0. Now the dipole moment for the one on the left hand side we can calculate, and we will get, after simplification, we will get that P vector is equal to 4QR x cap. But what about the one on the right hand side? So for this, we will get this expression. 0 is coming because the plus 2Q charge, it is at the origin, so the R vector will be 0. And if you simplify this, we'll get this expression. Now here comes the interesting part. In both the cases, the dipole moment are the same. And this is a very important property. That is, if the net charge is 0, then the dipole moment will not depend on the frame of reference. Let us take this example and let us try to find out the R dependence for this system. So we can use the same formula. Now in this system, the net charge is 0, so the monopole contribution will be 0. What about the dipole contribution? So let us first check what are the possible dipole moment which we can have. So we can have one dipole moment here, we'll call it P1. We can have another dipole moment here, we'll call it P2. And if you see P1 and P2, they are equal and opposite, so they'll cancel out. Similarly, we can have a P3 and P4. They are also equal and opposite, so they'll cancel out. So you can see that the net dipole moment for this system is 0. So the dipole contribution in the potential will also be 0. So the dominating term in this expression will be from the quadrupole term. So we can say that V is inversely proportional to R cube, and from this we can say electric field is inversely proportional to R to the power 4. Now there is also another variant where the 4-point charges can be arranged like this. Now let us see for this system. So we'll use the same formula. The net charge is 0, so the monopole contribution will be 0. What about the dipole term? Let us do a similar kind of exercise. So we'll have one P1 vector and we'll have one P2 vector. Now see, P1 and P2, they are pointing in the same direction, so they'll not cancel out. And we can have two more dipole moment. One is P3 here and another one is P4. So if you see the 4 possible dipole moments, they will not cancel out. So the net dipole moment will be non-zero. So the dominating term in the potential will be from the dipole term. So we can write V is inversely proportional to R square and electric field is inversely proportional to R cube. Thank you everyone for watching this video.